Welcome back, fellow fractal explorers. In our last episode, we introduced the basics of fractal geometry and its discovery by pioneering minds like Mandelbrot. We learned about the hallmarks of fractals like self-similarity, fractional dimensions, and infinite complexity. Today, we're going to venture out into the natural world to witness firsthand the abundance of fractal patterns in living systems and landscapes across scales. From the branching angles of trees to the rhythm of our heartbeats, we'll see signatures of fractal geometry everywhere. Nature leverages these fractal shapes for vital functions like maximizing surface area, optimizing networks, and generating endless diversity. Fractals reflect the way organic processes utilize recursion and feedback to build complexity. Understanding these natural fractal forms teaches us about life's intricate dances, and mathematically modeling them helps us recreate realistic structures. So get ready to zoom in on broccoli, soar over mountain ranges, and dive deep into your own fractal physiology. Let's explore why fractals fill the forests and flow through our veins. Our first stop on the Natural Fractals tour is the ragged edge where land meets water, the fractal coastline. In the 1960s, Benoit Mandelbrot analyzed the contours of Britain and found that the coastline length depends on the scale of measurement. Use a mile-long ruler, and you'll measure one length. Use a yardstick, and the length is longer due to detecting more twists and turns. This statistical self-similarity results from the coast carving through complex landscapes, with bays, cliffs, and inlets forming across scales. Mandelbrot proposed that coastlines have fractional dimensions reflecting this. Similar fractal geometry appears in the branching shapes of rivers and tributaries. Just as magnification alters measured coasts, so too for rivers as smaller rivulets appear under a microscope. Nature's edges elegantly display fractal contour. Beyond the ocean's edge, fractal patterns also abound in landscapes, from the curves of rolling hills to craggy mountain peaks. Mathematically, the roughness of mountain skylines can be modeled using fractional Brownian motion, a stochastic process that generates statistically self-similar fractal terrain. This technique can realistically simulate mountains, cliffs, and other natural landforms. In aerial views, the branching streams and tributaries of river networks snake across the land in fractal dendritic patterns to efficiently carve out the terrain. The self-similar splitting allows covering area while minimizing channel lengths. Fractal geometry also appears in wind-blown sand dunes, where the roughness behaves statistically similar across scales, and in the puffy geometry of clouds, which have fractal boundaries from turbulent air currents mixing moisture. Clearly, the forces shaping our planet's surface, erosion, fluids, gravity, wind, generate repetitive patterns across scales. Fractals reflect nature's recurring handiwork in sculpting landscapes. Beyond the landscape, the other dominant visible structures in nature are plants and trees. Here, too, fractal patterns abound due to efficient growth algorithms evolved over eons. The branching architecture of trees and leaves optimizes light harvesting and structural integrity through recursive fractal splitting. Models reproduce these natural patterns using L systems, which apply repeating rules to generate self-similar branching shape. In ferns, the placement of leaflets on the rachis mirrors the pattern of fronds branching off the rhizome underground. This self-referencing geometry gets reflected above and below ground. The spiraling florets of Romanesco broccoli and cauliflower demonstrate dazzling fractal arrangements to maximize space filling. Their conical repetitions illustrate exact self-similarity. Plants leverage fractal shapes in clever ways to replicate structural motifs across scales, pack more productivity into finite space using fractal branching, and build recursive patterns to fill areas. Fractals offer tested blueprints for optimal organic growth. Zooming into the wonders of the human body, we find fractal geometries underlying our very anatomy, from the airways in our lungs to the networks of our nerves. The bronchial tree that branches through our lungs does so in a fractal pattern to maximize surface area for oxygen absorption. This respiratory tree fractally divides over 20 generations down to the alveoli. Our circulatory system forms a fractal network to efficiently distribute blood by branching arteries into smaller capillaries, then back into veins. The flow through this vasculature is turbulent and exhibits fractal dynamic. Even our heartbeats fluctuate in a fractal manner. The intervals between beats show self-similar patterns across timescales, described by a fractal dimension, from organ systems down to tissues and cellular processes. Fractal scaling laws enable efficient performance. Our bodies contain fractal signatures of health beyond plants and people. Fractal formations permeate the rest of the animal kingdom and natural world, showing nature's endless creativity. In mollusks, the exoskeleton displays fractal grooves that increase strength and surface area. In coral reefs, the fractal branching maximizes habitat. The dragonfly's wing contains fractal patterns that improve aerodynamics. Seahorses have anatomies full of square spirals. In nest building by birds, bees, and termites, the recursive architectural patterns create stable, insulating homes using simple behavioral rules. When ants follow pheromone trails and bees traverse flower patches, their flight patterns show fractal properties to efficiently find resources. Across ecosystems, fractal networks appear in predator-prey dynamics, population distributions, and energy transfers. Fractals reflect nature's propensity for self-organized complexity. Wherever we look in the natural world, fractal shapes and networks enhance life through simple recursive rules, generating beautiful complexity. As we've seen, fractal patterns truly are everywhere in the natural world, from coastlines to mountain ranges, plants and physiology, animals and ecosystems. Nature is full of self-similarity across scales. Fractal geometry reflects life's innate tendency to build complexity through simple recursive rules and feedback processes. These shapes optimize growth, enhance function, and create diversity. Studying and modeling natural fractals mathematically is helping us better understand living systems and recreate realistic structures in computer graphics and engineering. In our next episode, we'll explore some of the mathematical techniques used to intentionally construct different fractal shapes for insights into their infinite complexity. Until then, keep noticing fractals when you're outdoors among the trees and clouds. Appreciate that your own body contains these beautiful repeating patterns, evolved for optimal health, and ponder how mundane rules can beget such marvelous complexity.